Okay, so this question asks us to use the information in the table and calculate the value of the rate constant, and we're given this reaction right here. So this is one of those problems where the first thing we need to do is we need to use this experimental data to come up with the rate law. And once I know the rate law, then I can calculate the rate constant. That's the steps we need to take. And it's not real explicit in this table, but what we've got here is a comparison of 3 different experiments. So these are experiments 1, 2, and 3. Okay? Now I'm going to show you a couple different ways to approach this. The analytical approach and then just the more formulaic calculational approach. So we know that in general a rate law, this reaction has 2 reactants. It has reactant A and reactant B. And so if I wanted to just write the generic form of the rate law, it's going to be that rate is equal to the rate constant times the concentration of A raised to some power we'll call X times the concentration of B raised to the some power that we'll call Y. And the first thing I need to do is I need to compare 2 experiments where one of the reactants is held constant and the other one is changed, so that I can see how the rate changes with the change in that concentration. And so I can do that if I compare experiment 1 to experiment 2. Notice that B stays the same. Concentration of B in both experiments is 0.3, but the concentration of A changes. It goes up from 0.15 to 0.45, and that caused a change in the rate. The rate went from 3.38 times 10 to the minus 5th up to 1.01 times 10 to the minus 4. All right, so I'm going to do this one just by analysis so that you can see how I approach that, and then I'll do the next one the calculational way. So I noticed that, or I can tell that this went up by a factor of 3. Okay, 0.15 times 3 is 0.45. So let's see how much the rate went up by. Since this is constant, since 0.3 equals 0.3, I know that this change in rate is due to this change in concentration of A. So let's see what factor this rate changed by. So what I'm going to do, I'll get my calculator out, and I'll do a ratio of the bigger number divided by the smaller number. So 1.01 exponent minus 4 divided by 3.38 exponent minus 5. Now hit enter. Okay, and see how it went up also by about a factor of 3. That's important. So the concentration went up by a factor of 3, and the rate also went up by a factor of 3. So remember, if I have a number and it on the other side is going to be equal to itself, what exponent do I need to substitute x with in order to make the 3 a 3? Well, 3 raised to the power of 1 is 3. So that gives me the order of the reaction in A. It's first order in A. Okay, it's first order in A, so x equals 1. All right. So now what I can do is I can utilize that information, and I'm going to, like I said, I'm going to do it the more calculational way to figure out this exponent y. So I know that if I want to compare experiments 2 and 3, and why would I do that? Well, in that case, the concentration of A stayed the same, 0.45 and 0.45. Because that stayed the same, and this changed. It went from 0.3 down to 0.15, down to 0.15. All right, and that caused a change in the rate. The rate changed. Okay, so I'm actually going to do this in kind of the reversed direction. I'm going to compare experiment 3 to experiment 2. And why am I doing that? Because in that case, if we just change the direction, the concentration of B goes up by 2. 0.15 times 2 is 0.3. Okay, and then this also goes up. All right. Now, like I said, I could just figure that out analytically the same way I did for A with this ratio, just taking the ratio of those 2 numbers. I take the ratio of those 2 numbers. But let me just show you the more formulaic way, just to kind of recap both methods of solving these kind of problems. So